Hey, welcome. We talk a lot about AI, but have you ever stopped to wonder how you actually build one that works? For a real business problem? Well, it turns out the answer involves a mix of hardcore science and some really high-stakes decisions. Today, we're going to dig into some amazing research that uncovers not just one, but two really surprising secrets to getting an AI to perform at its absolute best.
All right, so let's start by looking at a massive, real-world problem that pretty much every big company faces: customers leaving. In the business world, they call it customer churn, and trust me, it's a constant and very, very expensive headache. And to get a sense of the scale we're talking about, just look at this number. That's right, $4.7 trillion. That's roughly the annual revenue of the entire global telecommunications industry. Now, when your industry is that huge, even a tiny fraction of customers leaving adds up to billions of dollars in lost cash. The stakes are just incredibly high.
So what exactly is churn? It's really simple. It's just that moment a customer decides, I'm done, and cancels their service. But here's why it's such a killer for businesses. Getting a new customer can cost up to 20 times more than just keeping an existing one happy. So you can see why companies are absolutely desperate to predict who's about to leave so they have a chance to step in and win them back.
And of course, this is where AI is supposed to save the day. The idea is you train a model to spot all the warning signs. But there's a really sneaky problem hiding in the data itself that makes this whole prediction game way harder than it sounds. So let's get into this core technical challenge.
The number one hurdle is something called class imbalance. And if you think about it, it makes perfect sense. In any given month, most of your customers are perfectly happy. They stick around. Only a really small percentage actually decides to churn. So if you're an AI trying to learn what leaving looks like, you barely have any examples to study. It's kind of like trying to teach an AI to find a super rare orchid in a giant field by only showing it thousands of pictures of plain old grass.
And this chart just shows you how crazy that imbalance can get. In one of the datasets the researchers used, only 1%, one of the customers had churned. The other 99% stayed. Now here's the kicker. An AI trained on that data could just guess everyone stays over and over again and be 99% accurate, but it would be completely and utterly useless for solving the actual problem. Okay, so to tackle this imbalance problem, researchers basically set up a big competition, kind of like an AI bake-off. They took a bunch of different AI models and paired them up with different special techniques that are designed to fix unbalanced data. The race was on to find the absolute best combination for predicting who's going to leave.
And here are our main players. In one corner, we've got two heavyweight AI models, Random Forest and XGBoost. Both are famous for being prediction powerhouses. And in the other corner, we have three data balancing technologies, SMOTE, Edison, and GNUS. What these do, in simple terms, is they look at the very few examples of customers who left and then intelligently create a bunch of new, synthetic, or fake examples that look just like them. It's a way of giving the AI more to study from. So the mission was crystal clear. The winner of this bake-off wasn't going to be the model that was just accurate overall. No, the winner would be the one that was laser-focused and the absolute best at spotting that tiny but incredibly important 1% of customers who are heading for the exit.
And wow, the results were not even close. This chart here shows you what happened in that really extreme 1% churn scenario. The combo of the XGBoost model and the SMOTE balancing technique just blew everyone else away, scoring a 92% on a really important metric. The next best competitor couldn't even break 60%. This was a total knockout victory.
So case closed, right? We've got our winner, XGBoost plus SMOTE. Well, not so fast, because there's a little detail in the research paper. The model that won was a tuned XGBoost, and that one little word, tuned, opens up a whole second and maybe even more interesting question about how we build great AI.
So yeah, what does it actually mean to tune an AI model? This is where we pivot from asking what model to use to asking how you squeeze every last drop of performance out of it. And the answer is something called hyperparameter optimization.
The best way to think about it is this. An AI model is like a super complex machine with dozens and dozens of knobs and dials on it. These are its hyperparameters, and they control everything. How fast it learns, how complicated its thinking can get, you name it. Finding the absolute perfect combination of all those settings is what takes a model from good to great.
Now, for a long time, the standard way to do this was something called grid search.
And on the surface, it seems totally logical, right? You just pick a few settings for each knob, and then you patiently and methodically test every single possible combination. It's exhaustive, it's structured, and it feels like the proper scientific thing to do.
But what if that super logical, methodical approach is actually a trap? What if being that rigid is actually worse than just being a little bit random? And this is where we get to the second huge and really counterintuitive insight from this research.
This quote from a really famous paper from 2012 just nails it. The big idea is called low effective dimensionality. All that really means is, even if your AI has, say, 20 different knobs you can turn, for any specific problem, it turns out only 2 or 3 of those knobs are actually going to have a big impact on performance. The rest of them, they're basically just noise.
Okay, so take a look at this, because it shows the problem perfectly. This is grid search. Let's pretend the most important knob, the one that really matters, is on the bottom axis. You can see because grid search is locked into its rigid grid, it wastes a ton of time testing unimportant settings up and down, while only trying 3 unique values for the one setting that could actually change the outcome.
Now check this out. This is random search. With the exact same number of tests, see the 9 dots? It's not stuck in that grid, it's free. And that freedom lets it explore 9 totally unique values for that all-important setting. It's not wasting time on useless combinations. It's spending its time exploring more of what actually makes a difference.
So when you put them side by side like this, it becomes so obvious why random is better. For the exact same amount of work, the same number of trials, random search is way more effective at exploring the things that actually matter. It's not about being messy or chaotic. It's about being way more efficient with your resources.
And that brings us to our second huge takeaway today. When you're trying to find the best settings in a really complex system, sometimes a little bit of randomness is actually way more powerful and way more efficient than a super rigid logical plan.
Which kind of leaves us with this final mind-bending thought. To build these incredibly smart, logical AI systems that we want, maybe we need to embrace something that feels totally illogical. In this whole logical world of AI, could it be that one of our most powerful tools is actually just a little bit of chaos?